Hi everyone, welcome to my second year annual review meeting. I would like to present my progress report so far regarding my PhD topic, the cause of roughness predicting the direct penalty of the fault ship's hull. And as an introduction, nowadays there are more than 64,000 vessels worldwide with more than 500 gross tonnage or medium size. And as a comparison, here is our ship for this research, and the largest container vessels could reach more than 400 meters in length and with the capacity up to 200,000 gross tonnage. And this industry consume more than 400 million tons of fuel yearly, and this contribute to 200 billion US dollar per year and 3 to 4 global greenhouse gas emission. So what has the hull roughness got to do with this? And for a clean ship hull, and then 80 to 90% of the total drag comes from the skin friction. And then here is the example how clean is the ship's hull when I and Bagus visited Semarang shipyard in March 2022. And after several years of sailing, the hull will be covered by heavy calcareous fouling, and which it will increase by more than 40% in total hydrodynamic resistance. And then why do we have to predict the drag penalty of the ship's hull? And then this allows the ship's operator to estimate the excess fuel usage and schedule the appropriate time for dry docking, so they can send the ships to dry dock for maintenance at the optimum situation. And if there is a roughness on the ship's hull, and then there are two questions, and then how can we get the roughness topography from the ship, and then how can we determine the drag penalty of the ship. And we need a dive inspection. So, and then this is a common practice in a maritime industry. So in this case, let's the diver use the Unimelt image based underwater scanner, and then so they can measure the roughness topography, and then the researchers are able to reconstruct the 3D topography of the roughness. And if we already have this 3D scan of the topographical roughness, and then how can we determine the drag penalty? Then let's consider there are two ships here, and then these ships have the same speed and the same length. And then the first ship has a smooth wall, and the second ship have a rough wall. And then we quantify the rough wall with the equivalent sand grain roughness as a roughness currency, and the operating ships and also the KS will be the input for this drag penalty estimation. And then let's see the turbulent flow over a long flat plate with a uniform roughness by Pullen et al. 2017. And then we can assume the majority of the ship's hull now is like a cargo tank or tanker, like a cargo or tanker ships are of flat plate. And then here's a fixed curve of the epsilon here. It's represent the roughness of the ship's hull. And then for the x-axis here is the operating ship's condition. And then if we assume both of the roughness scenario here have the same area, and then let's say the rough wall is on this line, and then the smooth wall is on this right line, so that we can estimate the drag penalty from this scenario. And of course we don't want to let the ships completely rough until this point, because the ship needs to burn more fuel due to the drag penalty. And so on this simple workflow we can estimate the drag penalty of the ship. And unfortunately that we have a roadblock of this research. At present there is no reliable methodology for determining KS directly from a surface scan of the ship's hull, and there are several predictive correlations based on topographical properties such as McDonald, Chen, Furohi, and Fleck et al. And then the problem is most of these predictive correlations stated in a low effective slope and skewness, which doesn't represent the roughness from the biofoulings. And the KS cannot be measured directly, and it can only be estimated by exposing the rough wall to the fluid flow at various Reynolds number. So because of these roadblocks, let's say we need to bypass this, and then let's say we already have the 3D dimension of the reconstructed hull topography, and then we need to replicate and rescale the rough hull here, and then we need to conduct a wind tunnel experiment to exposing the rough wall to fluid flow, and then we can estimate the KS, and then we can continue the full scale drag prediction. And then in summary, there are two research questions here, and first is how to relate the topographic scan of the ships to the equivalent sand grain roughness, And then we need to improve the existing predictive correlation here for the realistic roughness based on the 3D scan. So in the future, we can bypass this laboratory process to estimate the KS. And then the second is how accurate the full-scale drag penalty estimation. And to validate this, we need an actual KS and drag based on the operating vessels and also based on the existing topographical roughness. So to answer this second research question, we have a research collaboration with PT Samudra Indonesia. So we have MT Sinar Morotai ship as the object of this research. And it's been sailing for 2 years since the dry dock, and we continuously monitor the drag penalty of the ships, and then we inspect the ship's hull through the dive inspection to validate the full-scale prediction. And what's going on the ship? So during the dry dock in March 2022, on the 69 meters downstream from the bow, we installed a marine grade window as an access for the LDA, or laser Doppler anemometry. So by utilizing this LDA, we can measure the boundary layer of the ship's hull, and by analyzing this data, we can determine the KS and the drag of the operating ship. So since dry dock in March 2022, we have 5 years opportunity to conduct field measurement on the ship until 2027. And thus far, we conducted 3 field measurements based on this talk by Yela at IPS DFD, and plus one that has been done this month, in this April. And we still have 3 years opportunity to continue this measurement. And the ships have been sailing for 2 years, and then the delta U remains constant around 4. And then what's the mean of value what's this value means to the ship? And these are responsible for the KS equal to 0.152 millimeters, which correspond to 28% drag penalty compared to the smooth wall. And then what causing the drag penalties? We need to check the dive inspection results. So in March 2022, we captured the rough surface imprints from these marks on the hull, and then we try to check what's changing in this mark over time. And then this is from November 2022, and this is from the January 2023, the second field experiment. This is from the third one on the June 2023, and the last one on this month in April 2024. And the anti-fouling paint layer seems to work very well here. We can see since the dry dock until now, there is no indication of hard fouling such as tube worm and barnacles. And yeah, if we see at June here, we can see more visible slime since June 2023. And on this April, what's going on? We can say that the hull starting to lose its anti-fouling paint, anti-fouling coating. And yeah, because there's an indication of the hull starting to lose its anti-fouling coating in the next 3 years, we expect that there will be an increasing delta U plus, or that means there will be a hard calcareous fouling growing on the ship's hull. And unfortunately, that we still don't know when exactly the ship will start fouling. That's why we need to keep continuously monitor this change. And during dry dock in March 2022, we have 5 imprints from various spots under the ship's hull, and we scanned these imprints with laser scanner. And then we also calculate the roughness statistic, and we need to quantify the KS of this paint job roughness to check the contribution of this roughness to the LDA measurement. And then this is based on our decision last year. We based on these 5 surfaces, we choose 1P based on the mean value of the roughness statistics among the others. And what do I have to do to estimate the KS from these imprints? So I need to fill 1 by 4 meters area with this roughness topography in the wind tunnel. And to perform it, there are several steps that I did. And from the raw scan, I need to tiling the surface. Then I need to carve the surface by CNC machine. And then finally, after I put all of the plates in the wind tunnel, I can do the measurement. So before I can do the tiling process, there are several steps that I need to perform. And here is the imprints, and then here is the raw result of the laser scan. I cropped some the original scans here, and I applied FFT filters to flatten the surface, and then here is the results. And during the imprinting process here, there are air bubbles trapped between the imprints and the ship's hull. and we can see it clearly here, and this bubble doesn't represent the real roughness. Then I remove it by replacing this bubble with two-dimensional cubic interpolation to the surrounding area, and then here is the result, and we no longer have the bubbles. And after we remove the bubbles, and to perform the tiling process, I initially determine the total desired area of the product. Let's say, for example, I want it to be 4 by 4, and then I select a random area and rotate smaller patch area to fill this area. And then in these blank spaces, this is where it is the places where I blended two surfaces to create a seamless tile here. And the final product of this process, it will be an aperiodic surface like shown in this figure, and the roughness statistic we maintain plus minus 2% difference compared to this process scan. And then here is the output from the tiling process for my scenario. So it's a 200 by 200 millimeters periodic test plate, so this plate will seamlessly connect to the next plate in any direction. And if we look at this paint job roughness, it has a low features of roughness height. So at this point, it's hard to replicate this roughness precisely with CNC machine. And furthermore, we also want to drive this roughness up to fully rough in the tunnel. Otherwise, we'll measure this surface that might looks like a smooth wall. And we carefully scale up this by maintaining the lambda over delta as low as possible. Otherwise, that there will be something weird as reported in Bagus in 2020. Then we agree to scale up this surface by 5 times to help this achieve a fully rough behavior compared to the unscaled version. For this scale up value, we will have lambda over delta around 0.19. And the geometrical scale-up ratio here will change the size of the roughness height while maintaining the same skewness, kurtosis, and effective slopes. And this scale-up ratio will contribute to scaling up the drag linearly by 5 times as reported in the existing predictive correlation. So I need to scale up this value by 5 times, and then the output product will be 1 by 1 meters of roughness surface. And then I can continue to the CNC process. Then I can start cutting this test plate, and here is the samples. I also analyze and optimize the cutting parameters by predicting the cut result from the G-code for the and then I got that I need to carve this roughness by using 2 millimeters diameter of the ball nose with 0.26 millimeters resolution. And with this setting, the produced roughness have a plus minus 3% difference in the roughness statistic compared to the original data. And to carve all of these plates, it requires 3 weeks without trial and error, and it's cost around 2,000 Australian dollar acetal plates as it for the raw materials here. Yeah, and then after I finish cut all of the plates, I have to arrange it in the tunnel. And then in the tunnel, if the flow will form a boundary layer here, and then at 3.8 meters downstream from the inlet of the wind tunnel, I measured the drag from this area with the drag balance, and also I measured the boundary layer with a constant temperature anemometer. And here is the drag balance result, and this is the first year task of my study. This is a smooth wall drag balance validated with the oil film interferometry as my baseline data. And then here is my I plotted the raw data of the drag balance experiment, which were repeated 9 times, 9 iteration, and it looks scattered. That's why I took a mean value from 9 iteration to interpret the result. And then here is the plus minus 4% error determining NCF, or the error bar. So based on this figure, we have a big problem. This curve doesn't show a fully rough behavior. So the CF is still developing by increasing the RE unit. And if we assume at the highest RE unit will form a fully rough, and this will correspond to 0.066 millimeters. And in the second scenario, I also need to estimate the KS by predicting this developing CF up to fully rough behavior. And then in this case, I try to plot a constant curve of KS on X based on Poulin et al. 2017 as a function of KS on X and REX is equal to CF. And then this value, it's from KS1X for the 5x surface 0.19, and the KS for the unscaled surface is 0.038. It's showing a lower value when we assume that it will form a fully rough behavior after this point. So, and then our average KS from the LDA measurement is 0.153, and then both of these assumptions show us how different the lab experiments compared to what we measure on the ship's hull by the LDA. So here is the hot wire result. I plotted boundary layer in the form of Z plus and U plus, and the U tau I got it from the drag balance result, and then the epsilon or the virtual origin I got it from the Clauser fit, and I varied the measurement into force speed 28, 25, 15 meter per second, and I also double check by plotting the turbulent intensity and also velocity deficit. They are collapsed very well in the outer region and in here along the line, indicating that the measurements perform in a good way. And to estimate the KS, I extract the delta U plus from the boundary layer here, and I would like to plot this value versus K RMS plus multiplied by C or KS plus, because I need to estimate the KS plus based on this plot. And the black dashed line is a Hama roughness function, and the K RMS of this surface is 0.182 millimeters. And here is my delta U plus versus K RMS plus, and then here is the error bar for determining the delta U plus, and then the error bar for determining the KS plus. The majority of this uncertainty is from the determination of the skin friction velocity and determining the virtual origin. And what I plot here is when my KRMS plus is equal to KS plus or C equal to 1. In the ideal scenario, I need to drive my surface up to KS around 10 power 2, and then I can see my data with asymptotically collapse to the Hama roughness function, because my surface have a low KRMS here, and then I'm only able to achieve the KRMS plus up to 10. So I need to estimate my data up to fully rough by fitting the constancy here to match the developing KS plus versus delta U plus. And in this case, I need to shift my data to the left or to the right depending on my assumptions. In my first assumption, I need to move it to the right, so I try to fit the highest delta U plus to collapse the Hama roughness function here, assuming that the data after here will collapse to here, and then it will increase the KS value if I shift it to the right. And unfortunately, that the data trends don't show that it will asymptotically in this way, and then I tried to fit my data to the generalized Colebrook function from Hutchins 2023, and then so that means I need to shift it to the left, and then in this case I need it will produce lower KS value than if I move it to the right. And then I also try to fit the P from the Colebrook generalized Colebrook into my data, and then I need to shift it more to the left, resulting more lower KS result. So in conclusion, that failed to drive the roughness to fully rough, resulting in high uncertainty to estimate the KS. So in summary, here is what we measured on the ships by the LDA. It produced 0.153 millimeters, showing the average KS. And then the lab result is way lower here, around the blue curve, which comes from one surface that we used before. And our current conclusion that the lab result do not represent what we measured on the ships, or maybe the LDA measured another roughness elements such as a deteriorated coating or like slimes, which correspond the case up to 0.1 millimeters or more, or maybe the LDA measured another roughness elements that we need to double check. And I still have my homework that I need to do in my third year of study, that I need to reduce this uncertainty of the lab result, and here is the option that I have. I can quickly test another surface from 5 frames to check this variation, and I can also try to rescale the test plate, which is gonna be painful, and then in order to create rougher surface, so maybe it will be easily to achieve fully rough. And then I can also modify the tunnel to be faster to increase the Reynolds number, and I can also use another facility. And regarding the field experiments for my third year study, first I need to process all of the dive inspection data. While the overall ship's hull are still clean from this video, there is a docking blocks marks that were not recorded during the dive inspection, causing its falling faster than the overall area. And then here is the video conducting the 3D scan of the docking blocks, and we already have the 3D scan of the area. And then we also tried to reconstruct it quickly, and here is the sample of it. And then I can also start the lab experiment of estimating the KS of the realistic roughness of the ship's hull. And however, ideally I should do it when the overall hull starts to default, then we can compare it to the LBA results. And from this video of the dive inspection, I can also try to create a map of heterogeneity. And then of course I need to continuously monitor the drag of the ships and the roughness state of the hull, and improving the data analysis of the LDA. So here is again chart that will show my third year research plan. In the first year of my study, I've spent my time for preparing for the first field experiments, and I also conducted 2 field experiments and 2 dive inspection. Then in the lab, I'm mostly working on OFI and drag balance. And for the second year, I did 2 field experiment and 3 dive inspection, and in the lab I've spent my time mostly on estimating the KS of the recently cleaned ship hull. And here is my position now. And then here is my research plan for my third year of my study. So first I need to continue the lab experiment quickly here to reduce the uncertainty from the previous one. And then I also need to continue to do the field measurement. And for the next lab experiment, and I can start conducting a realistic bay of falling roughness based on the 3D scan. And now I'm preparing, thus far I'm continuously writing a draft for publication from these results, and I'm planning to attend to 2 conferences, IPS, DFDN, and FMC. To close my presentation, here are my highlight photos from every time I visited the ships from the dry dock since 2022 until this month. And thank you.